authentication, such as end-to-end encryption with TLS, but the metadata about messages is still leaked to network observers. So when we have anonymity with metadata, what we want is metadata privacy. So what we build in Trellis, it's an anonymous broadcast system with metadata privacy. And it looks something like this. So you'll have senders who will send messages into Trellis, and then Trellis will output those messages onto the bulletin board. What we want to happen is that each message on the bulletin board should have equal probability of coming from any of the senders in the view of the adversary. And when that happens, we say that the messages are unlinkable to the senders. Specifically, Trellis will be a network of servers that are going to forward messages between them to implement anonymous broadcast. In fact, the adversary is going to control some of these servers. They're going to control a constant fraction of the servers in Trellis. So for example, if f equals 0.3, that means the adversary controls at most 30% of the servers. This adversary is going to be able to observe all the network traffic, including that important metadata, and there could be some number of colluding users that work with this adversary. So how do we make Trellis? Well, the starting point for Trellis is actually the mixed-net, which comes from Chom way back in 1981. In a mixed-net, you have a series of servers, and they're arranged sequentially. What you do with the mixed-net is you'll submit your messages to the first server. The server will shuffle the messages, forward them to the second server, will shuffle the messages, forward them to the third server, and so on. You'll note that the work in the mixed-net is that each server has to touch all M messages, and then forward M messages, and this happens N times. The mixed-net, though, however, is very robust. So as long as at least one of the servers in this chain is honest, they'll ensure that the messages have been shuffled and mixed and therefore are anonymous. So what we want in Trellis is we want this robustness. We want the messages to be posted even when lots of the servers are adversarial. But what we also want in Trellis is scalability. So the problem with this mixed-net is if we started adding more servers, it'd actually take longer and longer because all these servers have to keep sending all the messages. We want the performance to improve with more servers. That seems like a reasonable thing to ask for. And here we also want to scale linearly with the number of messages. The mixed-net does this, but there are other solutions that scale quadratically, and we're not interested in something that's going to scale quadratically in the number of messages. And finally, we need metadata privacy. We need the anonymity, even when the network is being observed. And so here, these first two properties are often in conflict. So we saw with the mixed-net, it was actually easy to get robustness, and that's because every server touched every message. It had a complete view of all the messages in the system. But if we want something scalable, that can't happen. We can't scale if every server has to touch every message. Every server has to have an incomplete view. It can only see some of the messages in the system. And so achieving both of these properties together is going to be a challenge. So let's say that we try to build something scalable. So we can look at parallel mixed-nets. So in a parallel mixed-net, what you're going to do is each server is going to have a subset of the messages. Then they're going to randomly divide that subset among the other servers. So they'll split it up and send it off to the servers. Each server is going to do this, and you're going to end up with a pattern that looks like this, which kind of shuffles the messages. You're going to repeat this pattern several times until the messages are shuffled. And this is very scalable. As we add more servers, each server has to do less and less of the work. Of course, this is not robust. Some of these servers are controlled by adversaries. So let's imagine that your message was supposed to take this path through the parallel mixed-net. But this first server happened to be an adversary. What this adversary could do is they could just not forward your message. They just wouldn't send it to the other servers. And what would happen is your message would no longer be output. This is actually a privacy problem because in the future, you might decide to resend your message, and now your message would appear. By dropping your message, the adversary knows who you are, and then when your message appears, the adversary knows that was you. And so here, you'll note that the servers, they didn't know what messages they were supposed to get because of the parallel mixed-net design. In the basic mixed-net, each server knew to expect all the messages, but here the servers don't. And so the first new tool we introduce in Trellis is the anonymous routing token, which is going to solve this problem. The anonymous routing token is going to allow servers to know which envelopes to expect. And with an anonymous routing token, a server will be able to anonymously check that an envelope is received from each assigned user. I won't go too much into the details in this talk, but the form of the token is a series of random values, and this is unlinkable to the user because all the tokens look random. But with the token, a server is able to check that it receives an envelope for whatever user created this token, even though it doesn't know that user. So now, what happens here? So a server later down this path will know that it was supposed to get an envelope that it didn't get. And it'll be able to report that fact. Okay, so who is to blame for this deviation? So what the server should do is, in fact, it should blame the previous server. And we're going to look at why that is. So the reason is that deviations are always going to be caught at the next honest server. So if this server in the middle drops it, then the next server, well, it says, I didn't get the envelope for the token. And so what this server will do is it'll blame the previous server. And you might ask, how do we know it is actually that server? So let's suppose it was actually the server that was 2 before it. So what should have happened is, in fact, if the server in between was honest, it should have reported it earlier. So before server 2 sends any messages to server 3, it should send the error message. It should say, hey, I have a problem, before it starts giving server 3 more envelopes. And if it was honest, it should have done that. But it didn't do that. So what does that mean? That means this server actually was also an adversary, because an honest server would have already blamed. And so what this means is that we can just blame the previous server still, this colluding adversary. So all we're going to guarantee is that one adversary server is removed for each server deviation. And by doing this, it bounds the number of times the adversary can deviate, because the adversary actually has a limited number of servers. Okay. But we have to do one more step here, right? Which is you can't take the word for it that someone dropped the envelope. You have to prove it. And so in Trellis, we make sure that every fact can be proved using publicly verifiable evidence. For this scenario, the evidence is pretty simple. What we're going to do is we're going to digitally sign each batch of envelopes a server sends. So if server 1 sends 7 envelopes to server 2, it's going to sign the concatenation of these envelopes along with it. And what this will allow us to do is that servers will be able to prove what the input they received was. So as a server, I can prove my input, and then I can prove that I performed the correct actions given that input. And so here I could prove that an envelope was missing or malformed, because it won't be present in the signed message I received. And so in particular, if like this, if the adversary dropped the message, the next server will reveal this signed envelopes and also this token showing that the token and the envelope the envelope is missing for that token. And if an adversary tries to invoke this, well, the honest server won't have signed the envelopes where the envelope is missing, so it won't be able to do this. And there's another thing that we want to note here was it actually okay to reveal all this information? And in both cases, it actually will be, because the adversary actually already knows the information. Because the adversary is one of the 2 servers on this link, and it already knows what was sent on this link. And so we don't actually, it's okay to reveal it. Okay. So once we have this evidence, we can decide which servers are honest. And the way we do this is we make this observation that honest servers will always evaluate this evidence correctly. So if we look at like this as a dispute, there'll be some servers that agree with blaming some server and some that disagree. And all the honest servers will actually be on one side of this dispute here. And so what the honest servers should do is they should just refuse to work with the servers who evaluate differently. And furthermore, because we ensure the evidence is publicly verifiable, users can also verify the evidence. And that means the users can choose to route through the honest servers in the future. And since every deviation will remove at least one malicious server, we'll eventually converge to the set of honest servers. And so we can actually support even a dishonest majority. Okay, so I talked about all that. But you might ask, how did these servers get these anonymous routing tokens? How do they know which users are even assigned to them? And so the second new technique that we introduce in Trellis is called boomerang encryption. Boomerang encryption is actually an extension of onion encryption, which you might be familiar with from other systems such as Tor. And so to briefly go over onion encryption, you're going to have a message and you're going to encrypt it repeatedly to each of the servers. And what each server is going to do is they're going to remove one layer of encryption and then forward the inside to the next server. So here there are 3 layers of encryption. Server 1 can decrypt the outermost layer, forward the inner 2 to server 2, who can decrypt 1 layer and forward it on. And the point here to notice is that all layers of decryption must be removed to get the message. So you can't go around any of these servers. In order for the message to pop out there, the message had to travel to server 1, who had to decrypt it, and then to server 2, who had to decrypt it. And so in boomerang encryption, we're going to extend this idea. We're going to encrypt with onion encryption along the path, and then back again in the other direction. And what this will do is it will provide a delivery receipt. So the user here will know that its message has been delivered because it receives the onion encryption receipt back. And only if all the servers along the path decrypt the envelope will the correct receipt be able to be returned. And so what we do with this is we use the boomerang encryption to obtain receipts that the anonymous routing tokens were delivered correctly. We show in our paper that you can do this incrementally in a process we called incremental path establishment to deliver anonymous routing tokens to all the servers on your path. Then these anonymous routing tokens guarantee delivery in later rounds. After that, we can do broadcast rounds where we deliver the actual payload messages along the established paths. You can see our paper for the full details. And throughout Trellis, there might be deviations. And for these deviations, we develop blame protocols that trigger on demand. These blame protocols will remove malicious parties with evidence. They'll discard malicious messages with evidence. We also show how to recover from deviations, and you can see our paper for full details. Okay. So now we get to the evaluation. So for our evaluation, we use AWS. We use up to 256 M5.X large machines, and we spread them across 4 AWS regions, Oregon, Frankfurt, Virginia, and Stockholm, to roughly match the Tor network geographic distribution. We also simulate limited bandwidth and latency conditions because you might notice about this design that the tail latency will greatly impact the time before we can send the next layer. And so for comparison, we use the state-of-the-art mixed network for this robust and scalable idea, and that's Atom. And so Atom is also limited by how to achieve robustness in their performance. And what Atom does is they use any trust groups. And any trust group is just a group of servers that's large enough so it contains at least one honest server with high probability. In this group, what it will do, the servers will just check each other work, and the honest server will keep the other servers honest. And the problem with this is that it has large computational overheads. Because we need anonymity and privacy, these proofs actually have to be zero-knowledge proofs. And so they'll take a long time, especially as the messages get large. Furthermore, as the group gets larger, all the servers have to check all the members of the group. So this also grows. In Trellis, the servers only check signatures. And so this is a very cheap operation in comparison. And in Trellis, when there's a deviation, the malicious party will be removed. Our protocols remain efficient for large messages, and we can support a dishonest majority where more than 50% of the servers are controlled by the adversary. And so when we compare Atom to Trellis, on, say, large messages, we see many orders of magnitude improvement going from years to hours. When we look at the scaling with the size of the messages and the number of messages, we see that the scaling is nearly linear. And here I show also that as the adversary fraction increases, as you expect, it takes a little bit longer, but not too bad. So here is f equals 0.1, where 10% of the servers are controlled by the adversary, 0.2, or 20%, and 0.3, or 30%. Where things get interesting is actually when we look at the server scaling. We find that Trellis is actually network bound. So what I mean here is that even as you add more servers, it doesn't help you send messages between layers. There's still a latency there. that is fixed. Furthermore, as you add more servers, you actually need to add more dummy envelopes between every pair of servers. So what do I mean by this? Is that we actually want metadata privacy, and that means we have to make two things happen. We need dummy envelopes as cover traffic to and between servers, and we need the servers to wait for other servers to send them envelopes to hide timing information. And these end up being inherent for building metadata private systems. Okay, so you can see our paper for things I haven't covered. We cover how to use trust graphs to manage a dishonest majority and to handle unresponsive servers who don't actually send any messages in a layer. We show how to derive the number of layers that are required to achieve mixing, and we provide full details on our blame protocols. I'll now take any questions.
Thanks for the talk. In 2005, I published an attack on parallel mixing that noticed that if you know where some of the input-output mappings lie, so if the adversary also supplies some of the inputs in addition to running the mixes, you can reduce the anonymity of the system. Have you looked at that attack, and do you know if it defends against your system as affected?
Yeah, so the way we prove the number of layers is we actually assume that only 2 of the users are honest, and that the rest are possibly controlled by the adversary. So I think that would cover your attack.
Okay, thanks. I'll take a look at the paper.